Okay, continue to look at this. We have a set, and inside of this set, the vectors follow this rule. Is this H? It is a vector space, right? So it says use either an approximate theorem to show that it is a vector space, or find a specific example to the contrary. Well, we have a lot of ways to do this. The first one is, to be a vector space, zero vector must be part of it, and clearly no zero vector. Okay, so already proved. Two, suppose we take a vector u, let's see, 1, 0, 0. Okay, vector v, let's see, 0, 1, 0. And clearly, if u plus v is going to give you 1, 1, 0. And noticing that this one does not belong to H. This u belongs to H, v belongs to H, but u plus v does not belong to H, okay? Third way, still keep the same u. So if we set, take a random scalar, let's say c equals 7. So c times u is going to be 7, 0, 0. And clearly, cu does not belong to H, right? Because 7 plus 0 plus 0 is 7. It's not equal to 1. So hence, it's not vector space. Okay. All right. Number 6. So give me a matrix with dimension m by n. So if we have this, A11 up to A1n, AM1 AM here. So keep in mind the column space of matrix A. It is the span of all the column vectors, right? So this is going to be a subspace of R of n, right? And then while the null space, you are looking for, right? So you're looking for the collection of vectors that will in other words, you're looking for the solution of this homogeneous equation. So clearly the null space is going to be the subspace of R of n, right? Okay, so this one's simple. Okay, cool. Keep going. Number 7. It's given this set that includes those following vectors. This set is a basis for R3. Justify your answer. Well, to be a basis for R3, you have to make sure that first those set are all linearly. The set is linearly independent. Okay. 2, span of this set, let's see, H is equal to R3. So only you have to satisfy both, and then you can claim that, okay, this is a basis. Well, it's very easy to see because this is a problem that it's the same pieces from problem 3, right? So as you can see that. We know that, so suppose we call this the V1, V2, and V3. Since V3 equals 2 times V2, so it's not linearly independent, so hence it is not a basis, and then done. So it's super simple. Cool. Now, next one, we are trying to we have a matrix here, all right, and then we have the row equivalent matrix, which is a echelon form, and then it asks us to figure out what is null space, the basis for the null space, column space, and the row space here. Okay, so when you're trying to find the basis for column space, you need to be extremely careful. That is, we write down this basis here. It's going to be based on the column from the original matrix A here. And then the way to figure out its basis is to figure out, okay, what is the corresponding pivot column. So as you can see that the first column, it is a pivot column. Second one is also a pivot column. So correspondingly, the vectors, column vectors, corresponding to the pivot column or the pivot position is going to become the basis for the column space. So this one, as you can see, is going to be -2 to -3, and 4, -6, and 8. Okay, so that's it. Now what about the basis for the null space? Well, let's do the row space first. Well, regarding to here, things become different. When you're trying to figure out the basis for the row space of this matrix A here, what you can do is you can construct this basis from the row equivalent matrix. In other words, we can directly read it out from the row equivalent matrix B. And the rule is, if you're trying to figure out the basis, it's going to be all the row vectors except the 0 vectors here. So as you can see, the row 1, it's not all zeros. Row 2 is also not a 0. So the basis for this row space of A is going to be counting to 1, 0, 6, 5, and then 0, 2, 5, 3. Okay. Okay. And then lastly, the basis for null space of A here. What you need to do is, you need to do a little bit extra work, because this row equivalent matrix is given, but it is not in the reduced echelon form. You need to do something to make it into a reduced echelon form, which is super simple in our A. So the reduced echelon form, let's see if we call it matrix C. So it's 1, 0, 6, 5. As you can see, it's going to be 0, 1, 5 over 2, 3 over 2, 0, 0, 0, 0. Basically, it's just divided 2 or multiply a half to row 2, and that will make to be this reduced echelon form. You got this, and then what we can do is you see x3 and x4, those are two free variables. So as you can see, x1 equals to -6x3, -5x4, x2 equals -5 over 2x3, -3 over half x4 here. So our, because the null space, it is exactly the set of the solution, including this the homogeneous equation, right? So if we write it down, x1, x2, x3, x4, easily you can see that they're going to be counting to x3, so -6, -5 over 2, 1, 0, plus x4, So it's negative 5, negative 3 over 2, and then 0, 1. And clearly, you know, the basis for the null space is going to be those two vectors, right? So the basis for this is going to be negative 6, negative 5 over 2, 1, 0, and negative 5, negative 3 half, 0, 1. Okay? So that is going to be the basis for the null space. Okay? So hope you enjoy this. Thanks.